In the previous lecture, we have discussed on the design of helical compression spring and we have solved a simple problem on that. In this lecture, I am going to solve another problem. Design a close coiled helical spring. So the meaning for close coiled helical spring is the spring is a helical compression spring for a service load ranging from 2.5 kilonewton to 3 kilonewton. The deflection for this load range is 6 mm. So actually in the problem, two loading conditions are given, and for this loading range, that is from 2.5 kilonewton to 3 kilonewton, the deflection is 6 mm. Using spring index of 5, that is C is equal to 5, take the shear yield strength as 700 Newton per mm square and modulus of rigidity as 8 into 10 power 4 Newton per mm square. Factor of safety is not to be less than 1.3. Also check the spring for buckling. So we'll start with the given data. So two loading conditions are given. The first load is P1, that is 2.5 into 10 power 3 Newton. Then P2 is equal to 3 into 10 power 3 Newton. Then del is equal to 6 mm. Okay, so remember that this del is the deflection from 2.5 kilonewton to 3 kilonewton. Okay, so C is 5, then tau y is given, that is 700 Newton per mm square. Then G is given, it is 8 into 10 power 4 Newton per mm square. Then factor of safety is finally given, that is equal to 1.3. Okay, so actually in the problem, the yield shear strength is given, also the factor of safety is given. So we can calculate the allowable shear strength tau is equal to tau y divided by factor of safety, that is 700 divided by 1.3, you will get 538.5 Newton per mm square. Then we have to calculate the P. Okay, so P is equal to P2 minus P1. Okay, so I'll tell you where to use the P2 value and where we have to use the P value. So be clear about it. So P is equal to P2 minus P1, that is 3 into 10 power 3 minus 2.5 into 10 power 3, that is equal to 500 Newton. Okay, so this 500 Newton is the load range, and for this 500 Newton, the deflection is 6 mm. Okay, so you have to be very careful about it. Since the maximum load, difference between maximum and minimum load is 500, in the problem it is clearly stated that the deflection for this load range is 6 mm. Okay, so when you calculate the deflection, then you have to use the load value as 500 Newton, but for calculating the shear strength, we have to use the maximum value, because we know that always we have to calculate the maximum stress value. So for calculating the maximum stress value, remember that you have to use the maximum load, that is P2. But for calculating the del, then we have to use the P value, because load is given for the deflection range. Okay, so del 6 mm is only for this 500 Newton. So we'll start with the calculation of dimensions. The equation is tau is equal to Ks 8 P2. Remember that here I have used P2 because for calculating shear we have to use the maximum load, C divided by pi d square. Okay, so Ks, the equation for Ks is given in the data book page number 7.100. You can write the equation, and in the problem the C value is given as 5. Substitute the values and calculate the Ks value as 1.31. Okay, so now you can substitute the value of Ks here, tau, then P2, C, everything, and you can calculate the value of the diameter. So the calculated diameter is equal to 8.8 mm, and we know that the C is equal to D by D. So further capital D can be calculated by using D is equal to C into D. Okay, so multiply the spring index with the wire diameter and calculate the coil diameter. Then the second step is calculation of number of turns. So del is equal to 8 PC cube n divided by GD. Here you have to use the P value because the deflection 6 mm is only for this 500 mm load range. Okay, so for tau 2 you have to use the P2 value, for del we have to use the P value. So substitute all the values. D we have already calculated, so that you will get the n value. N is equal to 9. The next step is total number of turns. Actually in the problem the end conditions are not given. So I am going to assume the ends are squared and grounded, and for squared and grounded ends the capital N is equal to small n plus 2, that is 9 plus 2, that is equal to 11. Then the fourth step is calculation of free length. So the equation is LF is equal to ND plus del max plus 0.15 del max. Okay, so N is total number of turns we have calculated, D is the smaller diameter. Here we have to calculate the del max. Okay, so actually the deflection given in the problem is not actually the maximum deflection. Okay, so maximum deflection means it is the deflection for the maximum load. Okay, so for a load of P2, what will be the deflection? That is your del max. But so del max is for P2 load, but del is for the load P. So actually in the problem the del value is given, so that is actually the deflection only for the load range P. It is not del max. So we have to calculate the del max value. So you can use this relation. So for P2 the deflection is del max, for P the deflection is del. So if you want to calculate the del max value, then keep the del max in the left side. Del max is equal to del by P into P2. So remember this relation. Okay, so in some problems they will give del max and they will not give the del value. So actually in this problem they have given the del value and we have to calculate the del max value. So remember this equation. So del max by P2 is equal to del by P. So for P2 the deflection is del max, for P the deflection is del. So if you want to calculate del max, bring the P2 to the right hand side. You know del P and P2. So the del is 6 mm and the P is the load range, that is 500. The P2 is 3 into 10 power 3. So the del max is equal to 36 mm. So actually this del max is if the spring is compressed to 3 into 10 power 3 load Newton, then the deflection will be 36 mm. Okay, so that is the meaning for del max. Okay, fine. So after calculating del max, you can substitute it here and you can calculate the free length. After calculating the free length, you can calculate the pitch, that is P is equal to LF divided by N minus 1. So the calculated pitch value is 13.82 mm. So after calculating all the dimensions, you can write the resulting dimension. Okay. In the problem, one more thing is given. So we have to check the buckling. So for buckling checking, remember that if LF divided by 4 is less than or equal to 4, LF divided by capital D is less than or equal to 4, then the design is safe. So if the LF divided by D is greater than 4, then the design is not safe. Okay. So here LF is the free length and D is the coil diameter. So in the problem, the LF is 138.2 and the capital D is 44. Okay. So these two data we have already calculated earlier. You can substitute that. If you solve this, you will get LF divided by 4 value as 3.14. Okay. And it is less than 4. So the design is safe. Okay. So two things are very important in the problem. One thing is the load variation. For calculating tau, we have to use the P2 value, and for calculating the number of turns, we have to use the P value, because here we are going to use del, not del max. Okay. If you use del max here, then you can use P2 here. There is no confusion about that. Then for calculating the maximum deflection, we have to calculate the del max. Remember that del max divided by P is equal to del by P. To calculate del max, you can substitute the remaining data and you can calculate the del max. Del max is the maximum deflection. Okay. So you can substitute that. Finally, for checking the buckling, the LF divided by D should be less than or equal to 4. Okay, fine. So this is how we have to approach the problem when the load range is given. That is, two loads are given. Okay. So the tutorial problem is a helical compression spring made of oil tempered carbon steel is subjected to a load ranging from 2000 Newton to 2500. So here P1 is 2000 and P2 is 2500. The axial compression of the spring over the above range is 5 mm. So the del for this range, that is actually del for the P2 minus P1. So for 500 Newton, the deflection value is 5 mm. Okay, fine. So the spring index is 5. Design the spring. Also check the spring for buckling. So for buckling, LF divided by D should be less than or equal to 4. Okay, fine. So here, one thing is very important. The material properties are not given. The tau value and the G value is not given. So G, we know that for standard material, we can assume the standard modulus of rigidity value. So you can refer the previous problems and you can consider any one of the G value. And for spring material, the tau will be in between 400 to 450 Newton per mm square. So you can assume any one of the shear stress value in between 400 to 450 Newton per mm square. So this range is actually for oil tempered carbon steel. So for oil tempered carbon steel, the tau will be in between 400 to 450 Newton per mm square. You can assume any one of the value in between that. So remember that for calculating the tau, you have to use the P2 value, and for calculating del, that is for number of turns, you have to use the P value, and while calculating the LF, you have to calculate the del max by the ratio, that is del max by P2 is equal to del divided by P. Okay. So these three formulas are very important. So it's an important problem.